Hello guys, so we are going to continue the discussion with respect to encoder and decoder sequence to sequence architecture. Already we have seen how it exactly works. We have seen the architecture with its complete in-depth intuition. But let us go ahead and let us try to understand the problems with encoder and decoder architecture, sequence to sequence architecture. And we'll just try to understand the problem, and in order to solve that particular problem, what we are specifically going to use and what architecture change will specifically happen in this encoder decoder sequence to sequence architecture, that also we will be seeing in the upcoming video. So let me just go ahead and let me quickly go ahead and create a generic structure again. So this is my encoder, right? Now with respect to the encoder, you know that let's say I'm using LSTM. So over here I have my LSTM, here also I have my LSTM, and similarly here also I have my LSTM. Let's say with respect to time, I have just drawn t is equal to 1, 2, 3, 4, right? And here you know that we specifically use embedding layer. So here I'm going to basically use an embedding layer. So embedding layer, okay. Now with respect to embedding layer, here we are going to give x11. Let's say this is just for the first sentence, x12, x13, and this will basically be my x14, which is end of sentence, okay. Now you know that this entire information will be going over here in the terms of vectors. So here a vector will be created. Here also a vector will be created based on this embedding layer. Here also a vector will be created. And finally here also vector will be created. Okay. Now when we are discussing specifically with respect to this, you know that here whatever output we are going to get, okay, we do not consider this. So here the final output will be considered, which will basically be my W. Let's consider this as W. This is my context vectors, right? And usually this context vector is represented by your two important lines. One is your long-term memory cell and your hidden state. So I will just combine this specific line over here, right? And this line only needs to be forwarded to the next decoder, right? So with respect to any use cases which has this entire encoder and decoder architecture is usually solving a sequence to sequence problem statement, right? So here let's consider this is my decoder, and here again I will be having my LSTM, okay, and let's say in this case I'll just go ahead and draw 3, right? So what is basically going to happen, this entire line will get passed to this, okay, and here I will again pass my SOS, let's say start of the sentence, okay. I will get my output. This state will still be passed till the last layer, but this particular output over here, let me just go ahead and create this. This will basically go ahead and pass through a softmax activation function, right? And with respect to this softmax activation function, I'm going to get the output. Then this output will further get passed to the input to the next LSTM. Similarly, this will get passed over here. Again, with respect to the output, I will again go back to the next one. And finally, I get my last output, which may be my end of sentence, right? And this will be my y hat, right? It can be y1 hat, y2 hat, right? Now, this is the entire architecture of an encoder decoder, right? But now let's focus on this context vector, okay? So when I say this is my context vector, I'm also considering it over here itself, because there will be two lines that will be passing, right? One is my CT, one is my HT. Okay, I will, if I combine both of them, this exactly becomes the context vector, right? So that is the reason why I'm representing this, because I'm just going to consider the output of the last LSTM with respect to time. Let's say this is the last time where I'm getting the sentence, so this will be the context vector. But understand what is the importance of this context vector. This context vector represents the entire sentence, right? This entire sentence that we are passing, right? Now, if this is a smaller sentence, right, this context vector will be more than sufficient to represent this particular sentence. But what did researcher do? Researcher, when they were testing, right, they used sentences of varying length to test it, right? Sentences of varying length. right? And they used a performance metrics. Again, if you go ahead and see the research paper with encoder and decoder, this research paper was something related to BLEU score, okay? And here on the left hand side, this will basically talk about sentence length. Now, when they use this encoder decoder architecture, you could see that they drew a graph which looks like this, right? That basically means as the sentence length kept on increasing, after a certain point, over here, let's say this is 30, 40, 50, and the sentence length went till high, the accuracy started decreasing. The BLEU score started decreasing, right? And this specific score is the performance metrics to test how your model is performing with respect to sequence to sequence data. Sequence to sequence data, right? So this was the problem. And why this is specifically happening? Because understand the context vector that we are probably considering, we are not taking this output, right? We are not taking this output. Instead, we are just taking the last output, whatever context vector it is basically creating. Now, this context vector, will have more information with the nearest word that is just passed in this particular timestamp, in the nearest timestamp. If this is my T4, T is equal to 3, T is equal to 2, T is equal to 1. You will be knowing that this context vector will have more information about those words which will be to the nearest timestamp, right? At T is equal to 4. But what about at T is equal to 1? And if my sentence keeps on becoming bigger and bigger, let's say if this is T is equal to 100, if there is T is equal to 1, this single context vector will be having more context information of the recent words that are there with respect to the timestamp. But what about those words that came at T is equal to 1, T is equal to 2? It will have less context because here the context vector will be having limited information about it. So the context vector that is used to represent the entire sentence will not be sufficient, right? And that is the reason why for longer sentences, the BLEU score was very, very less. And this was the problem with the encoder and decoder sequence to sequence architecture. So how do we specifically fix this problem? For fixing this problem, we have another new amazing mechanism which we will be talking about, which is called as attention mechanism. And this attention mechanism, we will talk regarding it, sequence to sequence networks. We'll try to understand the architecture in the next video, what exactly change we really need to do in this encoder and decoder, because this is my encoder, right? This is my decoder. The work is very simple. My encoder will encode the information and my decoder will decode back that particular information. That is why we use cases like text generation, sentence generation, language conversion, right? Different kind of use cases. So we will try to understand what exactly is this attention mechanism. Just to give you a brief idea, right? Whenever we have a longer sentence or longer paragraph, along with this context vector, right, that we are specifically passing, we will pass additional context. How do we pass this additional context? We'll see about it. What architecture diagram will be changing, we'll see about it. But just to give you an idea, here is the research paper that we will be discussing about. Neural machine translation by jointly learning to align and translate. And over here, if you go ahead and see this architecture, this is my encoder, this is my decoder. We will be discussing about this particular architecture and how this architecture is different from the previous one. Here you can see in the encoder, you just don't have only one LSTM layer. You also have bidirectional LSTM layer. So here also you have this, here also you have this. And then you probably combine all the information. You pass that additional context to your decoder. And that is what we are going to go ahead and have a look, right? And then we'll be understanding about each and every equations as we go ahead, right? Because whatever output you will be specifically predicting with respect to the decoder, here you will be having the context of the previous state. You will have this additional information that is probably coming up. And along with that, whatever you will be your previous output, that will also be there, right? So we will try to combine all those things and we'll try to see. But before that, let's go ahead and see. And I hope you have understood what is the problem with respect to your encoder and decoder sequence architecture. And that is what I'm going to discuss in the next video, where we'll discuss about attention mechanism, how we will provide some additional attention while training this entire models. So yes, this was it from my side. I will see you all in the next video. Thank you.